Alright, now, again, this is just another short screencast, probably 8 to 10 minutes, about conservation of specifically heat energy. Now, conservation of energy works for any kind of energy that you want to set next to set equal to each other. You can start with kinetic energy and turn it into potential. You can start with heat and turn it into kinetic. You can start with chemical and turn it into kinetic. You can start with electrical and turn it into potential. There's all these different things that you can do with conservation of energy. This one's going to focus specifically on conservation of just heat energy. Okay, so keep that in mind, that conservation of energy is broader than just heat, but I was focusing specifically on it for this particular situation. All right, and the first is heat cannot be created or destroyed. It's simply transferred between objects or converted to other types of energy. Okay, so as I said again, you can take heat and you can turn it into something else. That's how a steam engine works. An old steam engine takes heat and turns it into kinetic energy to move the train. So you cannot create it or destroy it. You're simply moving the energy around from place to place and from type to type. Okay, so the energy of the universe is steady. It's just being converted from one thing to another. Alright, now the first thing you have to understand is, in order for heat to be transferred between objects, they have to be in thermal contact to one another. Okay, with thermal contact requires actual physical contact. Alright, in order for you to pass, in order for energy to pass into your body, let's say you put your hand on the burner on top of your stove that's still on. Okay, so there's a hot burner on your stove that you put your hand on by accident. You have to physically put your hand on the stove in order for the energy to pass into your hand. Okay. In order for you to get cold, like let's say you get stuck outside and it's snowing and you sit down in the snow. Okay, you have to physically be touching that cold snow in order for you to pass your energy to the snow. Okay. So that's an important thing to understand, that thermal contact really is important when you're talking about energy loss and energy gained for heat. Okay, now the one other thing that is often misunderstood is that there's a direction of heat transfer is always the same. Heat always transfers from the object of lower temperature to the object, it always transfers from the object of higher temperature to the object of lower temperature, regardless of which one is larger and what they're made out of. Okay, that's a really important thing to understand. A lot of people think that the larger object gives its energy to the smaller one. It's the hotter one gives its energy to the cooler one. Okay, regardless of size or material or anything. Okay, there's no such thing as a flow of cold. It's always a flow of hot. Okay, so when you talk about the wind, for example. Okay, wind comes from a place of high pressure and temperature, and next to a place of lower pressure and temperature, and the heat is actually transferring from the place of high temperature to the place of low temperature, and that's where wind comes from. Alright, so if you feel a cool breeze, that's not because there's a cold air flowing. It's because the air that's flowing is colder than you, and you feel that change in temperature on your skin. It's not that there's cold air moving, it's that you're warmer than the air that's moving. Okay, a little confusing, but you'll get the idea. Now the math of it all, it's really simple. Just as in mechanical energy, the amount of energy lost is equal to the amount of energy gained. Okay, so usually you'll have on one side the object that's losing energy is the hotter object. The object that's gaining energy is the colder object. Okay, so you're going to actually see an MC delta T on both sides, or possibly 2 or 3 depending on how involved the problem is. Okay, so if you want to put ice in a glass of water, all right, the ice is going to be on the gain side because it's cold. It's colder than the water, and the water is going to be on the loss side. So you're going to have the Q of water on one and the Q of the ice on the other. Now, the thing that's most important to understand is that the Q's are always positive, okay, which means the change in temperature is always positive. So a good thing that you should write down in your notes while I'm saying this is that when you talk about the change in temperature for objects that are gaining heat, okay, objects that are gaining heat, you want it to be positive, which means it should be the final temperature minus the initial temperature. For objects that are losing heat, it's the opposite. The change in temperature should always be initial minus final. Okay, if you need to really think that out and write it down in your notes, I would. All right. Another way to look at it, for those of you that understand absolute values in math, the delta T in your equations is always the absolute value of it. Okay. Keep that in mind as you're going through it. Now, when does it end? The heat will continue to transfer until the objects meet the same temperature at the end. They will reach thermal equilibrium. They will have the same final temperature. Okay, so the heat is going to continuously be transferred until they meet that spot where the temperature is the same. Now, that doesn't mean, though, that it will be the middle point. Okay, if you have 20-degree water and you put it in with 100-degree water, it doesn't mean that they're going to meet in the middle at, what would that be, 60. Okay, it all has to do with how much you have. Okay, so just because you have something at 0 degrees and something at 100 degrees, when you put them together, they're not going to reach 50. They might reach a common temperature of 5 degrees if you have a lot more of the colder object. Okay, so don't just assume it's going to meet directly in the middle. It won't. But that term that we're talking about right now is called thermal equilibrium. All right, so I'm going to start using these terms more often, so I want you to understand what they are so you don't get lost trying to figure out what these terms mean while I'm using them in context of other things. All right, so let's try one. Let's see how you do with it. Okay, you have 2 kilograms of aluminum at 80 degrees is dropped into 25 degree water. Okay, so you're taking a block of aluminum that's hot and you're putting it in a big bucket of cold water. If the final temperature of both materials is 27 degrees, what is the mass of the water? Okay, so you have a bunch of numbers going on in here, and we're going to work through it. Before I say stop the video and try it, first think about what object is losing heat and what object is gaining heat. Once you have that, you can separate their values for them on each side. Okay, so if you're going to put the aluminum on the losing side, because it's going down in temperature, only values that attach to aluminum should go on that side of your equation. On the other side, the water is gaining temperature and heat, so only values that are attached to the water should go on that side of your equation. Okay, so everybody stop the video, work your way through it, and then play the video and see if you're right. Okay, you should have stopped the video, tried it on your own, and then worked your way through it. So here's the work. Now remember, it's Q lost equals Q gained, and the aluminum is on the left side losing heat because it's the hotter object losing temperature. Okay, that's why I have it on the left side underneath Q lost, as you can see. Now the way you find the Q of any object is like you saw in the other video, is the mass times the specific heat times the change in temperature. That's where that MC delta T of aluminum came from. On the other side, it's the same thing, except the water is going up in temperature. So it's the MC delta T of water, the mass of the water times the specific heat of the water times the change in temperature. So what I did was I put the numbers in. So you have aluminum, 2 kilograms. The specific heat of aluminum always is 900. And the aluminum is changing its temperature by 53 degrees. Okay, it's losing 53 degrees. And remember what I said earlier, the delta T is always positive. So I didn't have a negative 53, I just had a change in temperature of 53. Okay, on the other side, we don't know what the mass of the water is. So that's our variable. So that M on the water side, you want to leave it there. I know some of you like to put an X in there. That's your variable. The C of water, you know what it is. It's always 4,186 while it's liquid water. And then that side, it only changed by 2 degrees. Okay, so the water only changed by 2 degrees. It increased by 2 degrees. So what's the mass of the water? 11.39 kilograms. You do your math, multiply it out, and then divide. Okay, now if you need more help with that, you need to come see me in the morning, come see me at lunch, email me about this video, something like that. Let me know that you need more help. I can't help you if you don't tell me. All right, but you should be trying this on your own, in your notes, doing the work, and making sure you can get through it. Okay, now it's up to you to go ahead and try some. There should be some on Schoology for you to try. I'll make up some more. I'll make up as many as you guys need in order to get it down. Okay, if we have to do 300 of them for you to get it down, we will. We shouldn't have to, but if that's what we need to do, that's what we need to do. Okay?